Welcome to the Deep Dive, your shortcut to staying ahead, cutting through the noise, and getting straight to the core insights from the research shaping our future. Today, we're tackling a fundamental challenge. What's something that's really keeping AI agents from truly transforming our lives? Memory. Think about it. How can an AI actually remember ongoing conversations or, evolving business data, even the nuances of your personal preferences over long periods? It's a big hurdle.
It really is a huge one.
So our mission today is to unpack ZEP, which is this novel memory layer service built for AI agents and its powerful core component Graphiti. We're going to explore how ZEP tackles the persistent limitations of current large language model LLM memory, understand its unique architecture, and find out why it's not just performing well, but actually outperforming existing solutions in some pretty demanding real-world scenarios.
Yeah, and there are some surprising details in how this digital memory is evolving. Get ready for those.
Definitely. So we've all kind of bumped up against this context window problem in LLMs, right? That limited short-term memory. It means they eventually just, forget earlier parts of a long chat.
So exactly. It's like talking to someone and after 5 minutes they ask you something you literally just told them. They've lost the thread.
Right. And that makes it incredibly difficult for these AI agents to hold on to long conversation histories or integrate what we call out-of-domain knowledge, effectively.
Which leads straight to problems like the AI hallucinating information, making stuff up, or just flat out forgetting crucial details from past interactions.
And totally forgetting.
And, while retrieval-augmented generation, RG, has become pretty common for feeding LLMs external knowledge, current RG frameworks are mostly stuck with static document retrieval.
Okay, so if RG is like giving the AI a reference book,
Yeah.
it's a beautifully bound book, maybe, but the pages never change. It never gets new notes, never updates facts.
Precisely. And it certainly doesn't remember your ongoing chats or, say, how your business needs are evolving day to day.
That's a really crucial point, the static nature of it. So if the current methods are falling short, what does this continuously evolving data actually look like? And what kind of breakthrough does handling that enable for AI agents in, our daily lives?
Well, for AI agents to become truly pervasive, like actually helpful assistants that autonomously solve complex problems, they need access to a large corpus of data that's constantly evolving.
Okay.
Think ongoing user chats, related business data that updates maybe even dynamic world events. Current RAG approaches just aren't built for that dynamic future.
Right, just the sheer volume?
Partly volume, but mostly the change. Entire conversation histories, massive living business data sets, they can't effectively fit inside an LLM's context window. And even if they could, the model isn't really designed to process that constant flux internally. It's not just about adding more info, it's about adding info that changes.
Right, the dynamic aspect. And look, this idea of giving memory to LLM agents isn't brand new. We've seen concepts explored before. I think systems like MemGPT kind of paved some of the way here.
Yeah, MemGPT definitely explored this space, but ZEP is aiming to take it quite a bit further.
Okay, so ZEP is pitched as this novel memory layer service. How is it fundamentally different? What makes it novel beyond just, being another memory layer?
Well, the core innovation really is Graphiti. That's the engine inside ZEP. It's described as a dynamic, temporally aware knowledge graph engine.
Dynamic and temporally aware.
Okay, that's what lets ZEP move beyond just static data or simple retrieval. It's the secret sauce, if you like, that enables that fluid, evolving memory needed for really complex agent interactions.
So how does Graphiti actually, work this magic? You said it synthesizes unstructured and structured data.
Right. It takes in conversational data, business data, whatever, and weaves it into this knowledge graph. But the key is that it maintains historical relationships. It uses what they call non-lossy updates.
Non-lossy. So it doesn't just overwrite old facts.
Exactly. It doesn't just say your preference is now X. It keeps a record that your preference was Y until a certain date, and now it's X. It maintains a precise timeline of facts and relationships, including their periods of validity.
Wow. Okay.
So ZEP isn't just storing facts like in a database. It's building a living, evolving historical record of its knowledge.
Imagine an agent not just knowing your current favorite color, but remembering when it changed, maybe even why, based on past conversations.
That's the potential, yeah. Truly adaptive, personalized interactions over months, maybe years. It's a pretty fundamental shift in how AI could operate.
And it's built for the real world.
And crucially, yes, it's built as a production system. The paper emphasizes a heavy focus on accuracy, latency, and scalability for memory retrieval. It's designed to perform reliably in demanding environments, not just in a controlled lab setting.
What does that mean, practically speaking, being a production system? Are there specific architectural choices beyond Graphiti itself that make it robust for those real-world demands, not just lab tests?
Good question. It really means reliability and performance under load. It's things like efficient indexing, optimized query paths, handling concurrent requests. The engineering needed to serve that knowledge graph quickly and consistently.
Right.
The focus isn't just on the cleverness of the knowledge graph, but on the nuts and bolts of making it work fast and reliably, which is critical for any real-time AI agent.
Okay, that makes sense. Now, you mentioned Graphiti is like building this historical record. The paper also talks about it mirroring human memory. That's fascinating. Can you unpack that? How does Zepp's architecture actually translate concepts like episodic and semantic memory into, well, digital components? Are there challenges in making AI recall things in a human-like way?
Absolutely. It's a really interesting aspect. Zepp's structure draws inspiration from psychological models, distinguishing between episodic memory, like recalling specific events or conversations.
Okay, like what we discussed last Tuesday.
Exactly. And semantic memory, which is more about the associations between concepts, the general knowledge, like knowing Paris is the capital of France.
Got it.
To map this, Zepp's knowledge graph has three hierarchical tiers.
3 tiers. Okay, what are they?
So at the base, you have the episode subgraph, GS. This is where the raw input messages, text, maybe JSON data gets stored, non-lossy.
The raw log.
Think of it as the AI's detailed event log, yeah. Every interaction recorded accurately. This is the foundation, the ground truth from which semantic understanding is built. The paper focuses mainly on messages as these episodes in their tests.
Okay, base layer is the raw log. What's next?
Building on that is the semantic entity subgraph GS, that this layer processes those episodes to pull out entities, things like people, places, topics, key concepts.
The important nouns.
Kind of, yeah. And crucially, it also extracts the semantic edges, which are the relationships between these entities. And importantly, it resolves entities. Meaning, if John Smith pops up in 10 different messages, GHUS figures out it's the same John Smith, linking all those mentions together. It avoids creating duplicates and builds a consistent view of each entity.
Smart. Okay, so raw episodes, then semantic entities and relationships. What's the top level?
Finally, you have the community subgraph. GC, this is a higher level of abstraction. It represents clusters of strongly connected entities.
Clusters, like groups of related things.
Exactly. Think of them as communities of concepts or entities that frequently appear together or are strongly linked in the graph. These provide high-level summaries, a more interconnected view. It builds on ideas from things like GraphRag. It helps see the forest, not just the trees.
Okay, G, GC, AC, APE, E, high, episodes, entities, communities. That makes sense. So we've covered storage, but what about the timeline? You mentioned temporally aware. This bitemporal model in Graphiti sounds like a key differentiator. How does tracking 2 timelines give Zepp an edge?
It's incredibly powerful, yeah. This bitemporal model tracks 2 distinct timelines simultaneously. There's T, which is the straightforward chronological order of events when something actually happened in the real world.
Right, the event time.
And then there's T prime, or T, which tracks the transactional order when Zepp actually processed or ingested that information.
Ah, okay. Why track both? What's the benefit?
Because knowing when Zepp learned something can be as important as knowing when the thing happened. Imagine data arriving late or corrections being made. This lets Zepp understand not just the state of the world, but the state of its knowledge about the world at any given point. It can accurately reconstruct history, knowing precisely when a fact was considered true by the system.
That's subtle but crucial.
It's a novel advancement for these kinds of knowledge graphs, especially for LLMs. It provides much richer, more accurate historical context, which is vital in, say, fast-changing business scenarios where knowing the timing of information is everything.
And this precise time tracking enables Zepp's dynamic data management, which you said is a key feature. Let's talk about how it handles new info. For entity extraction, it looks at the current message and the last 4.
Yep, the current message plus the last 4 for context. And it uses this clever reflection technique.
Reflection, like looking in a mirror.
Sort of, yeah. It basically involves having the LLM double-check its own extracted entities, kind of like asking itself, does this make sense? Did I miss anything? It helps minimize hallucinations and improve the coverage of what it extracts. And then these entities get embedded for similarity search later.
Okay. And what about extracting the relationships, the facts?
Right, fact extraction. ZEP identifies the relationships between these entities, and this is where it gets interesting with hyperedges.
Hyperedges sounds fancy.
It just means an edge or relationship that can connect more than two nodes or entities. So instead of just Alice works at company X,
Uh-huh.
a hyperedge could represent Alice, Bob, and Project Phoenix are all associated with the Q3 launch. It lets ZEP model these more complex, multi-way relationships much more naturally than trying to break them down into simple pairs. Gives a richer understanding.
That makes sense for real-world complexity, which raises a big question. How does ZEP handle changes? What if a new fact contradicts an old one? Like if Alice stops working at company X.
That's where the temporal extraction and edge invalidation comes in. It's super important.
Okay.
ZEP extracts timestamps, both absolute dates like June 23, 1912, and relative ones like 2 weeks ago, and it normalizes them. But crucially, when a new potential fact, an edge, comes in, it uses an LLM to check for potential contradictions with existing facts in the graph.
So it actively looks for conflicts.
Yes, and if it finds one, like the new fact says Alice now works at company Y, the old edge, Alice works at company X, isn't deleted, it's invalidated.
Wow.
ZEP sets its TINVALID timestamp to reflect when that fact ceased to be true based on the new information. It always prioritizes the newest data as the current truth.
Wow. So it keeps the history. It knows Alice used to work at company X, but now works at company Y.
Exactly. It maintains both the current state and the historical record of how relationships evolved over time. It's like a living history book that's constantly being updated but never erases the past.
That is incredibly sophisticated, almost like an internal editor constantly refining its understanding.
That's a good way to think about it, yeah.
And what about those communities, the GC layer? Are they static once formed?
No, they're dynamic too. The community updates happen as new data flows in. ZEP uses something called a label propagation algorithm to adjust the community structures on the fly.
So they evolve with the graph.
Right. This dynamic updating is really efficient. It significantly cuts down on latency and the cost of running LLM inferences because you don't need to constantly rebuild the entire community structure from scratch. Though they do mention periodic full refreshes are still a good idea to ensure perfect alignment.
Okay, so ZEP stores knowledge dynamically, keep track of time meticulously. How does it actually retrieve that information when an agent needs it?
Right, retrieval. It's a powerful and highly configurable system. Basically, it's a function. You give it a text query, and it returns formatted context tailored for an LLM agent to use.
And it does this using a three-step process.
Yes. First is the search step, represented by Philly. This is about identifying all the potentially relevant nodes and edges from that vast knowledge graph.
Casting the net wide.
Exactly. And it uses multiple methods together, like a multi-pronged attack. There's cosine semantic similarity search, which finds things that mean something similar to your query, even if the words are different.
Okay, conceptual search.
Then there's a copy, BM25, full text search, which is more traditional keyword matching, finding similar words. Keyword search.
Got it.
And because it's a graph, it uses breadth-first search, BFS. This explores the connections around initial hits, looking maybe 1 or 2 hops away in the graph to find related information that might provide crucial context.
Finding things that are nearby or related.
Precisely. It can even use recent episodes, like the last few messages, as starting seeds for this BFS, ensuring recent context is explored. This whole multifaceted approach really maximizes the chances of finding the best possible context.
Okay, that sounds comprehensive. It's like using every trick in the book to find that one specific piece of info, or related info, in a giant library. So after this broad search, which is designed for high recall, getting everything potentially relevant, what's step 2?
Step 2 is the reranker, RU. The search step might pull in a lot of candidates, some more relevant than others. The re-ranker's job is to increase precision, to sift through those candidates and prioritize the most relevant ones.
Okay, sorting the results. How does it do that?
It uses various techniques, things like reciprocal rank fusion, RRF, or maximal marginal relevance, MMR, which are algorithms for intelligently combining and scoring results from different search methods.
Clever scoring.
It also uses graph-specific methods, like an episode mentions re-ranker that boosts info referenced frequently in past conversations, or a no-distance re-ranker based on how close things are in the graph structure.
Hmm.
And the most sophisticated option, though computationally heavier, involves using cross-encoders, basically,
Yeah.
smaller LLMs, to directly score the relevance of each piece of context against the query.
Using an LLM to rank results for another LLM.
Okay.
Okay, so search wide, then rank precisely. What's the final step?
The final step is the constructor, chi. This takes the top-ranked, most relevant nodes and edges selected by the re-ranker and transforms them into a structured text format that the main LLM agent can easily understand and use.
Ah, packaging it up for the agent.
Exactly. It provides the facts, importantly with their valid date ranges, thanks to the bitemporal model, entity names and summaries, maybe summaries of relevant communities. It gives the LLM exactly what it needs, formatted clearly, to generate an informed response.
Okay, that whole retrieval process search, re-rank construct,
Yeah.
sounds incredibly thorough. Now, connecting this back to the bigger picture, theory is great, but how does ZEP actually perform in practice? You mentioned benchmarks.
Right. The capabilities were validated using established LLM memory benchmarks.
First up was the Deep Memory Retrieval Benchmark, DMR, developed by the MemGPT folks.
That's the one. It uses 500 multi-session conversations, up to 12 messages per session. And here's where it gets interesting. ZEP actually showed superior performance.
Better than MemGPT on its own benchmark.
Yep, ZEP hit 94.8% accuracy versus MemGPT's 93.4% using GPT-4 Turbo. It also outperformed simple baselines, like just feeding the full conversation history, a solid early win.
Impressive. But there's a catch with DMR.
There is. And credit to the ZEP paper for pointing this out clearly. They found DMR has significant weaknesses. It's pretty small scale, only 60 messages total per conversation, which, as they note, easily fits within the context windows of many modern LLMs anyway.
So it doesn't really stress test the long-term memory aspect.
Exactly. Plus, it relies on fairly simple, single-turn fact retrieval questions. The paper argues it poorly represents real-world enterprise use cases, which are often much more complex and require deeper reasoning over longer histories.
Okay, so while ZEP did well, DMR wasn't the ultimate test of its unique strengths.
Correct. Which brings us to the LongMemEval, or LME, benchmark.
And this one is the real test.
This one is described as much more challenging and designed to better reflect enterprise use cases. It involves complex temporal reasoning tasks, and the conversations are long, averaging around 115,000 tokens.
Whoa, okay, 115,000 tokens. That's definitely way beyond standard context windows.
Absolutely. And notably, the ZEP team mentioned they couldn't directly evaluate MemGPT on this benchmark, likely due to the scale and complexity, which really underscores the challenge ZEP is tackling here.
So how did ZEP do on LME?
This is where the results are really striking. For accuracy, ZEP achieved substantial results with accuracy improvements of up to 18.5%. For instance, ZEP using GPT-4o got 71.2% accuracy compared to a baseline getting only 60.2%.
That's a big jump in accuracy on complex tasks.
It is, but maybe even more impressive was the latency. ZEP reduced response latency by a massive 90% compared to the baseline.
90% faster.
Yes, we're talking ZEP responding in about 2.6 seconds versus nearly 29 seconds for the baseline using GPT-4o. That's the difference between a usable real-time agent and one that feels incredibly slow.
That's game-changing for usability. How did it manage that speed up and accuracy gain?
Through context efficiency. Remember how the baseline had to process the full 115,000 tokens? ZEP, using its retrieval system, achieved these results while sending only a tiny fraction of that, an average of just 1.6K tokens to the LLM.
Wow. 1.6K versus 115K. Think of the cost savings on tokens alone, never mind the speed.
Exactly. Huge implications for cost and speed in production.
And digging into where on LME ZEP improved most. It excelled on the harder stuff.
Yes, the biggest gains were in the complex question types. Things like single-session preference questions saw improvements up to 184%. That's remembering user preferences within a long session. Temporal reasoning improved by up to 48.2%, and multi-session questions improved by up to 30.7%.
So exactly the areas where sophisticated, long-term, time-aware memory should shine.
Precisely. It shows ZEP's architecture is really delivering on its promise for those challenging, long context scenarios.
Was it perfect across the board, though?
There was one notable exception, as the paper calls it. ZEP actually showed a decrease in performance for simpler single-session assistant-type questions like basic instructions within the current turn. For example, a 17.7% drop with GPT-4o.
Huh.
Any idea why? The paper suggests it might need further tuning for those kinds of immediate, less memory-intensive tasks. Perhaps the retrieval process sometimes filters out immediately relevant info or adds slight overhead. It's an area flagged for future work.
Okay, fair enough. So what does this all mean for you, the listener, taking these results together?
Well, they strongly demonstrate Zep's effectiveness for actual deployment in real-world applications, especially anything involving cross-session information synthesis and long-term context maintenance. It's not just theoretical, it looks like a practical step forward for building more capable AI agents.
So to quickly recap, we've seen how Zap, powered by this Graphiti knowledge engine,
Right, with its unique graph structure using episodic, semantic, and community layers.
achieves really state-of-the-art results on memory benchmarks, especially the challenging ones.
And critically, it does this while slashing token costs and dramatically cutting down latency. Those are the metrics that matter for actually deploying these things.
Looking ahead then, this deep dive really shows how AI agents are starting to gain the kind of sophisticated dynamic memory that feels, well, a bit closer to our own cognitive structures.
Yeah, the ability to truly remember evolving contexts, your preferences changing over time, complex business data, the world around it, it feels foundational for whatever comes next in AI applications.
So let's leave you with a thought to ponder. Imagine the possibilities when AI agents can genuinely remember everything relevant, dynamically accurately, without needing us humans to constantly feed them info or sift through data.
How might that reshape whole industries? Think personalized customer service that actually knows your history over years. Or hyper-efficient business operations where an AI assistant has a perfect living memory of every project detail, every decision, every shift in priority.
What new opportunities does that unlock? Or perhaps what new challenges might arise from AI having such powerful, persistent digital memory?
Yeah, definitely something to think about as this technology keeps evolving and pushing the boundaries of what AI can really do.